Welcome to section 4.7, financial models. All right, objective number 1. Determine the future value of a lump sum of money. So exponential functions are used in a number of financial models. Before we look at some of these models, we should define some terms. Interest is the money paid for the use of money. So this means that when you deposit money in a savings account, the bank pays you interest because they're using your money. When you take out a loan, you pay the bank interest because you're using their money. Now, the total amount borrowed, whether by an individual from a bank in the form of a loan or by a bank from an individual in the form of a savings account, is called the principal. Think of it this way. The principal is your starting point. It's the original amount of money before any interest is added or changed. And the rate of interest expressed as a percent is the amount charged for the use of the principal for a given period of time, usually on a yearly, that is per annum basis. Theorem simple interest formula. So this states that if a principal of P dollars is borrowed from a period of T years at a per annum interest rate R expressed as a decimal, the interest I charged is I equals PRT. Now, why is this formula important? Well, this is the simplest way interest can be calculated. It's a straight multiplication, no compounding, no complexity, and you'll see this used for short-term loans and some basic calculations. All right. An important note, though, about variables. So note, we differentiate when a formula's variables are capital letters because certain letters are used for particular applications or values. For example, lowercase I is used in complex numbers and has the value -1. Lowercase p is often used in statistics. So a tip here for you is just to pay attention to whether variables are uppercase or lowercase in formulas because they mean different things in mathematics. So the interest charged according to the formula I equals PRT is called simple interest. Now, in problems involving interest, the term payment period is defined as follows. Annual is once per year. Monthly is 12 times per year. Semi-annually is twice per year. Daily is 365 times per year. Quarterly is 4 times per year. Why does this matter? Well, the frequency of compounding affects how much money grows or how much you owe. So more frequent compounding will equal more interest. So when the interest due at the end of a payment period is added to the principal so that the interest computed at the end of the next payment period is based on this new amount. So that's the old principal plus the interest. The interest is said to have been compounded. Now, compound interest is interest paid on the principal and on previously earned interest. Okay. So the power of compounding is important because this is why starting to save money early makes such a huge difference, because your interest earns interest, which is creating exponential growth. So let's look at an example for computing compound interest. So a credit union pays interest of 5% per annum compounded quarterly on a certain savings plan. If $2,000 deposited in the plan and the interest is left to accumulate, how much is in the account after 1 year? All right, so we're going to work this out step by step. So first, we need to use the simple interest formula to determine the amount after the first quarter. So that's going to be the formula I equals PRT. Okay. So we know that our 5% per annual compounded quarterly is going to be our interest rate. The $2,000 is going to be our principal. And our year, we want to know how much is going to be after the first quarter. So the first quarter is 3 months into the year. So 3 months into the year is 1/4. So we'll enter those values into our formula, multiply them, and we get $25. So what has happened here in our first quarter? Well, we calculated the interest for the first 3 months, which is 1/4 of a year, and the interest earned is $25. Now we're going to use the new principal and the simple interest formula to determine the amount after the second quarter. Well, we're going to then take the principal and we are going to add it to the interest that was earned. Well, our principal was $2,000. That's what we entered in at the beginning. And we earned $25 in the first quarter. So after the first quarter, we now have a total of $2,025. So now we want to know what is the interest that's going to be added to this amount after the second quarter. So we'll use our formula, I equals PRT. We'll use our new principal of $2,025. We'll multiply it by our interest rate and our time, which is still the next 3 months. And that gives us a total of $25.31. Notice that the second quarter earned more interest than the first quarter. The second quarter was $25.31, whereas the first quarter was $25. This is because we're now earning interest on the $25 we earned in the first quarter, and this is compounding in action. Okay. So now we can repeat this process for the third and fourth quarters. So for quarter 3, we're going to take the principal from quarter 2, add the interest that's earned, and we'll get a total of $2,050.31. Then we'll find the interest that's earned on this principal by taking I equals PRT, multiplying it by the rate and the time, 1/4, which is the next 3 months, which gives us an interest of $25.63. We will then continue for quarter 4 by taking our Before we go into quarter 4, we'll now take our principal, add our interest to find the principal that we have going into quarter 4, which gets us $2,075.94. And then we will take that value and find the interest. Again, taking our new principal, multiplying it by the rate and the time, and we get $25.95. So then we're going to add this new interest to our principal, and we get a total of $2,101.89. So that means the amount in the account after year 1 is $2,101.89. Okay. So rather than repeatedly calculating the new interest and adding that to the principal each quarter to find the new quarter's principal, we can use the formula in the following theorem. So why are we going to use this formula? Well, just imagine that if you had to calculate 40 years of quarterly compounding, that's 160 separate calculations. That's a lot of calculations. So this formula does it all for us in one step. So this theorem, the compound interest formula, says that the amount A after T years due to the principal P invested at an annual interest rate R expressed as a decimal, compounded N times per year, is A equals P times the quantity 1 plus R divided by N raised to the power NT. So breaking down this formula, we have A equaling the accumulated future value of the account. So this is what you'll have at the end. Then we have P, which is the present value. So this is what you will be starting with. All right. And then you also have N, which is the number of times per year the interest is compounded. You have R, which is the annual interest rate. Remember, that's always as a decimal. And you have T, which is the time in years. Okay. So we are going to use this formula and the values from the previous problem to solve for our future value. Okay. So in the previous problem, we started off with $2,000 as our principal. Our interest rate was 5%, so that's 0.05. Our time was 1 year. We wanted to know the total amount we would have in the account after 1 year. And our N is 4. Okay, remember, N is the number of times per year interest is compounded, and it was compounded every quarter. Okay. So when we plug these values into our formula, we get a total of $2,101.89, which is the exact value we got when we solved it step by step in our previous example. But you see how one calculation is way easier instead of 4. Okay. Now note, sometimes this value will be slightly different from the previous used in the previous, will be slightly different from the process used in the previous example due to rounding errors. Okay, but it's very, very, very close. All right. Okay, let's go to another example. So here we're investing $2,000 at an annual rate of 8% compounded annually, semi-annually, quarterly, monthly, and daily, with yield the following amounts after 1 year. So our P here, what's given to us, is $2,000. Our R is our interest rate, so that's 0.08, and our time is 1 year. So annually, N here would be 1 because we're compounding 1 time per year if it's annually. So we will substitute all of our given values into our formula for the compound interest, and we would then solve for our value, which is $2,160. Semi-annually, N here is 2, semi is 2 per year. Plug that into our formula. We'll get $2,163.20. Quarterly, your N is 4. Okay, plugging that in, we'll get $2,164.86. Monthly is 12. So the only thing in these problems that are changing is the N, and we get $2,166. And daily, we use the value 365. So plugging that into our formula, we get $2,166.56. Okay. All right. So what do you now notice about the final amount as you increase N? So as N is increasing, so from 1 to 2 to 4 to 12, and then to 365, what do you notice? Oh, let me go back. So the key thing that we notice is that as N increases, the final amount increases. So the key insight here is that more frequent compounding means more money. But notice the increases start getting smaller as N gets bigger. So going from annual to quarterly makes a bigger difference than going from monthly to daily. Okay. So if we continue letting the number of times we compound each year continue growing towards infinity, we'll end up with the following formula. So what does this mean? Instead of compounding every day or every hour, imagine compounding every second or every millisecond continuously. So mathematically, this is the limit as N approaches infinity. So our theorem for continuous compounding states that the amount A after T years due to a principal P invested at an annual interest rate R compounded continuously is A equals PE to the RT. So the number E is approximately 2.71828. It is a special mathematical constant, and it appears naturally in continuous growth problems. So in your calculator, this would be the button e to the power x. Okay. So when interest is compounded so that the amount after 1 year is PE to the R, the interest is said to be compounded continuously. So we're going to take a few minutes to review the derivation of this formula in the text to see how E ends up in this formula. Okay. So in our example, the amount A that results from investing a principal P of $2,000 at an annual interest rate of 8% compounded continuously for a time T of 1 year is, well, first we need to state what is given to us. What in our problem do we already know? Well, we know P is 2,000. That's our principal. We know R is 8%. So that's 0.08. And we now want to know what is our amount after 1 year. So T is going to equal 1. So plugging that into our formula, PE to the RT, we'll get 2,000 times E to the power 0.08 times 1, which will get us 2,166.59. Now, if we were to have compared this to our previous problem where we were compounding daily, that gave us $2,166.54. So continuous compounding gives us a higher amount. The difference is only 5 cents, but in practice, daily and continuous compounding are very similar. Okay. All right, let's go to objective 2, which is to calculate effective rates of return. So what is an effective rate? Well, the effective rate of interest is the annual simple interest that would yield the same amount as compounding n times per year or continuously after 1 year. So why is this useful? Why can't we just stick with the continuous compounding? Well, let's say that you compare different investment options on an apples to apples basis. So one bank might offer a 3.1% compounding monthly, and another offers a 3.15% compounded quarterly. Which is better? Well, the effective rate tells you that. Okay. So the theorem for the effective rate of interest states that the effective rate of interest R sub E of an investment earning an annual interest rate R is given by compounding n times per year. Our formula is 1 plus R divided by n raised to the power n minus 1, and compounding continuously E to the power R minus 1. Okay, so how do we use this? Well, we're going to calculate the effective rate for each option, and then we'll choose the highest one. That's how you would determine which one would be best. Okay, so let's do an example. So suppose you want to buy a 5-year certificate of deposit, so a CD. You visit 3 banks to determine their CD rates. American Express offers you 3.145% annual interest compounded monthly. The First Internet Bank offers you 3.15% compounded quarterly. We now need to Discover offers 3.12% compounded daily. Now we need to determine which bank is offering the best deal, okay, based off of what it is that they offer. So let's first do American Express. So American Express has an interest rate of 3.145, and it's compounded monthly. So our N here is 12. So we would use the first formula where it's compounding N times per year. So we will plug in R, we'll plug in N, and then we will find our answer to determine what this bank is offering. And it's offering a percent amount of 3.191% return on our investment. Now, First Internet Bank, the R here is 3.15% compounded quarterly, we will then plug in these values into our formula for the R and the N, and we get a return of 3.187%. And then for Discover, the interest rate is 3.12, and it's compounding daily, so N is 365. Plug that into our formula, and we get a return of 3.169. Okay, so we can see here that the effective rate of interest is the highest for American Express. So American Express is offering the best deal. So what is the lesson in this problem? Well, the lesson is that we should not be fooled by the highest advertised rate. Okay, so American Express had the lowest rate. It had a 3.145%, but the highest effective rate of 3.1917% because of the monthly compounding. Okay, so this is why this formula is very important for us to determine which one will allow us to get the highest on our return. Okay. All right. Objective 3, determine the present value of a lump sum of money. Okay. So the present value of $A to be received at a future date is the principal that you would need to invest now so that it will grow to $A in the specified time period. Okay. So a real question this answers is, I want to have $50,000 for a down payment on a house in 10 years. How much do I need to invest today? Okay. So that is a real world question that this present value formula will help us solve. So the present value of money to be received is always less than the amount to be received, since the amount to be received will equal the present value plus the interest accrued over the time period. So think of it this way. $1 today is worth more than $1 tomorrow because today's dollar can earn interest. So the present value formula states that the present value P of $A to be received after T years, assuming a per annum interest rate R compounded N times per year, is P equals A times the quantity 1 plus R divided by N raised to the power negative NT. If the interest is compounded continuously, then P equals A times E to the power negative RT. Okay, so note the difference. So these are just the compound interest formulas solved for P instead of A. Same math, just different question. All right, our example. A zero coupon, so a non-interest bearing bond, can be redeemed in 20 years for $5,000. How much should you be willing to pay for it now if you want a return of, and our first one here, 7% compounded monthly? So let's first identify what's given to us. Well, we know our A, that's our future value, and we want $5,000. Okay, our time here is 20 years. So we are now going to identify our R, which is 7%, and compounded monthly, so N is 12. So we're going to enter this into our formula for compounding in times per year. So we'll enter in our A, our R, our N, and our T, and we'll get an answer of $1,238.01. So that means for a return of 7% compounded monthly, we pay $1,238.01 for the bond. So if you pay this amount today and it grows at 7% compounded monthly for 20 years, you will have exactly $5,000 in your account. Okay? So that's what that means. Now let's do 5.5% compounded continuously. So we know our A is 5,000. We know our T is 20. Our R here is 5.5%. and it's compounding continuously, so we don't have an n. So our formula is a times e to the power negative rt. So we'll substitute in our a, substitute in our r and our t, and we'll get a total of $1,664.36. So for a return of 5.5% compounded continuously, we'll pay $1,664.36 for the bond. Okay, so that means the lower interest rate means you need to invest more today to reach the same 5,000 goal. So lower returns require bigger initial investments. Okay. All right. Objective number 4, determine the rate of interest or the time required to double a lump sum of money. Okay, so recall the following formulas for compound interest. Okay, so for compounding n times per year, we had A equals P times the quantity 1 plus R divided by n raised to the power n times T. And for compounding continuously, we had A equals P times e to the RT. Okay, so the challenge is when R or T is an exponent, we can't just solve algebraically. We will need logarithms. So what rate of interest compounded annually is needed in order to double an investment in 10 years? So we know that n equals 1 and we know t equals 10 because it says compounding annually, so n is 1, and we want to double in 10 years, so t equals 10. So we're going to take our formula for compounding n times per year. We will then substitute in the information that we know. So we know that we want to double what we invest in 10 years. So what do we invest? We invest P. P is our principal. So our future value A is going to be double our principal, or in other words, 2P. Okay. So we also know our N and our T. So we can substitute that in. So our N is 1 and our T is 10. So that would make our fraction just R, and then N times T would be 1 times 10, which is just 10. Now we can divide both sides by P because they both have a P. So now we have 2 equals the quantity 1 plus R to the power 10. Then we can take the 10th root of both sides. So we have the 10th root of 2 equals 1 plus R because the 10th root eliminates the exponent 10. Okay. Now we want to get R by itself because that's what we're trying to find. What rate of interest will allow us to have double our investment in 10 years if it's compounded annually? So we'll subtract 1 on both sides, and then we'll have to enter the right side into our calculator to get a percentage of 7.18%. Okay, so the annual rate of interest needed to double the principal in 10 years is 7.18%. So why does this work? Well, we use the property that taking the nth root is the same as raising to the power of 1 divided by n. So this undoes the exponent, allowing us to get to our interest rate of R. So now how long will it take for an investment to double in value if it earns 4.2% compounded continuously? Okay, so now we are doing continuously compounding instead of annually compounding. So we know our interest rate is 4.2%, so we have our decimal. And we know since we're continuously compounding, we'll be using the formula for compounding continuously, which is A equals P times e to the RT. Since we want to double our investment, which is our principal, we have 2P equals P times e to the RT. We can then enter in our R. Now we want to find T. We want to know how long it will take for an investment to double. So we need to find T. So we'll first divide both sides by P. Then in order to get our exponent out of the exponent location, we can apply the natural log to both sides. We can then move the power to the front of our natural log e, which then eliminates the natural log e because that equals 1. Divide both sides by 0.042. We'll enter that value in our calculator and we will get 17. So it will take about 17 years to double the investment. Okay. So why did I use the natural log? Well, the natural log is the inverse of e to the power x. So it undoes the exponential, just like the square root undoes squaring. Okay, so the natural log helped me here to get to t. So how long will it take to triple at this rate? Okay, so we're still compounding continuously. So we still have the same r and we still are using the same formula, but this time we want to triple our amount. So now we have 3p equals p e to the rt. We can substitute in our r. We can divide both sides by p, giving us 3 equals e to the power 0.042 times t. We can then take the natural log of both sides. We can move our exponent to the front of the natural log e, eliminating the natural log e because it equals 1. Divide both sides by 0.042. Enter the right side into our calculator, which gives us 27. So it will take about 27 years to triple the investment. Okay. An interesting observation between A and B is that it takes about 17 years to double and 27 years to triple. So doubling to tripling takes about 10 more years. So growth slows down as the base gets larger. Interesting.